Okay, it's time for the next session. I don't mind that you speak, so don't get me wrong. I would like this to be interactive if possible, but if not, you will have to keep up with me chatting. So yeah, I'm Ulf. I'm working in the kernel worker group in Linux. I've been doing that for quite some years and working with power management. This topic is about the support for multiple system-wide low power states, or actually the support that is lacking today in the kernel around this. And in particular, I'm talking about platform-specific states. But let's go into the details. So I will give you a very, top-level background to what we have today and the way things are working, just to get you into what I'm talking about. And then we will look into a couple of real use cases where we'll see where things aren't working, and then in the end we'll look into what we can do to make it work. So that's the plan. So what I mean with system-wide sleep is that the whole system goes into some low power state to save power. So typically, if you have like a laptop, you'll close the lid, and it goes into this low power state. Or if you have like a TV or a set-top box and press the power button, don't think so. It's not really turned off, it's just into a low power state. There's also another mechanism internally in the kernel that we call auto-sleep. That's like an opportunistic sleep where the kernel continuously tries to go into that deep system-wide sleep state, unless there is someone that actively blocks it. So, for example, in these Android devices, you can have the screen turned light on, and if you leave it for a while, it just goes into the system-wide sleep. So that's when Android has released its block for going into this deep state. So that's the two different ways of how it's being managed in the kernel today. So, speaking about those user space driven triggering mechanism, I just wanted to briefly show how it looks like today, just to give you a little bit more context. So we have a couple of SysFS nodes where this is being managed from. So for the top one here is the sys power state, and there's a couple of different states that you can strings that maps to a state that you echo into those nodes, and that is in the end the state that you will go to. So we have freeze, standby, and disk, and those are mapping to different things. Suspend-To-Idle for an ACPI 0, and for standby it's ACPI S1, and disk means hibernation. I don't know how much you know about this, but it's not really important to go into these details at this point, I think. One of the interesting part here is when you use mem. So mem is actually mapping towards what is been written in the mem sleep SysFS node. So if you have S2idle in that mem sleep node, mem mean S2idle. So if you have deep, it means suspend-to-ram. So it's like a way of, you can think of it as a way of adding more dynamical states here. But it's still quite static, so to say. And the other node that I have here also on my slide is the auto-sleep thing. So it's the thing I talked to you about with the Android thing. That's it's just mapping to the same state. It's just a different node to control the auto-sleep mode. So the observation I want you to pick away from this, that I know I also have done that, of course, is that these are all quite static things. And if we want to add more states or have this more dynamically manageable, in the end, what you could consider is to allow more of these strings in the mem sleep. But in the end, that doesn't really scale. It would be a lot of platform-specific strings, and we don't really want that, of course. That wouldn't work. So moving into some of these use cases. So this is just typical use cases that we have and how it's been supported today in the kernel. So what I'm trying to describe here in the left part is that, I mean, we have a PCI-based platform. PCI is the CPU power management interface that is common for ARM products. And that platform is supporting Suspend-To-Ram, S2R. And this only supports one state. That's the way PCI and Suspend-To-Ram is working. There's one state. So, well, it's fine, but it's one state. If we look at how Suspend-To-Idle is working, you can have a platform that supports multiple states, perfectly possible. So those states are being used in CPU idle during runtime, where we pick states based on latency constraints, more or less. But for Suspend-To-Idle, where we reuse those states, we always use the deepest state. So it's possible to have more states, but it's still only one that gets selected always. And the other typical use case that we have is like if we have like a power domain for SEMI power domain, for example, that may also support multiple idle states for that power domain, for that devices that it controls. So depending on latency constraints during runtime, we decide to go to different states. But for Suspend-To-Ram and Suspend-To-Idle, it's always one state. It's always the deepest states. That's how it's worked today. Any questions so far? Okay, just briefly summarize a couple of observations I've done and I wanted to share with you. So when we do Suspend-To-Ram, there is a couple of, let's say, constraints that we have to agree with the firmware, is that usually it's always the boot CPU that needs to be the last CPU, and you also need to hot plug or offline the other CPUs before you actually allows the system to go to that state. So that's like a contract between firmware and the Linux of how this should work. And obviously, taking CPUs like offline is not always that cheap. It takes some time to do that, and obviously you need to online them when you resume the system. So there's some latency involved there. There's also another observation for PCI. I mean, per the interpretation of the spec is that there is only one state available for Suspend-To-Ram. You could maybe extend the spec to add more, but this is the way it's today. With Suspend-To-Idle, we have less latency because we don't have to deal with this last boot CPU thing. So it means that any CPU can be the last one that goes into suspend. So it's simply quicker. There's no latency involved in regards to that. When it comes to S2I and PCI, there is also the possibility of supporting multiple states, as I just spoke about before. So, that said, let's go into more details of those use cases. But I guess you can already now figure out what I'm trying to point at. So it seems like S2I is a good option if we can make it work. It sounds reasonable to me. Okay, so let's go into some of the actual use cases. So these are use cases that has been brought to my attention by speaking to different vendors at various occasions. And this is actually a TI use case, a platform that TI has. So they have a power domain that is controlling peripheral devices, and that power domain has multiple states. The way we model this today is through the generic power domain framework in the Linux kernel. And if that power domain has multiple states, that's also been taken care of by this generic power domain framework. But the problem here is that, as I said, we always pick the deepest state when we go to suspend-to-idle. And for this particular platform, that becomes a problem. They have a whole bunch of different states, but they don't want to go to the deepest state because that breaks some latency constraints for a system-wide suspend. So if you go to those deeper states, you'll simply have longer time to bring back power to devices and power rails and restore states. So it takes too much time to meet those constraints. So that's one of those use cases. The other use case is more targeted towards automotive. And it's PCI-centric. So it means that we have multiple states being supported for this platform with PCI. And this platform, I don't know if you're familiar with PCI in those low-level details, but there's something that's called CPU suspend mode. So there's two different ways of how to do CPU power management. So there's something called OS-initiated mode and platform coordinated mode. And in this use case, both of those modes seems to be, used. You only use one at a time, but there seems to be reasons to support both scenarios, so to say. So the way this is working today and how this is being modeled in the kernel is that CPU-idle and GenPD's generic power domain framework is collaborating a little bit about how to select states. If it's only the platform coordinator mode, it's only CPU-idle that selects the state, but during suspend-to-idle, it selects the deepest states, and that breaks the system-wake latency constraints. And in the other scenario where we have OS-initiated mode, we might involve the generic power domain too. But even in that cases, when that power domain is controlling the CPUs and the states for those, it always selects the deepest state. So in both of these cases, there's problems of not meeting the system-wake-up latency constraints. So before I move on, I have just a few more slides. So if you have any other use cases or any other, situations that you can think of that kind of relates to this, I'm interested to hear about it. So if you don't, if you don't, if you don't tell me them now, just ping me later on, and I'm definitely interested to see. So we make sure that we don't, miss out on some pieces. So the possible solution, and I don't know how many people are involved in this kind of areas of the Linux kernel development, but from a top-level point of view, this is what I think we should do. So in principle, that generic power domain thing needs to be given a governor for system-wide states. So it can actually validate some constraints before it selects the states. And the similar is as I see, is for CPU-idle. CPU-idle has governors already, but those are only used during regular idle path. So if we could have another governor that is being used during suspend-to-idle, that could help this. And the other thing that we need is that we need user space to be able to specify this system-wide latency constraint. So what we have today that is kind of already there is something that is called CPU DMA latency. So that's an interface that is already available for user space, where it can specify the system-wide latency constraint. Today, it's not being used for system-wide suspend. It's just being used in various drivers and various the regular idle paths during CPU idle. So I'm thinking that maybe we could use this for system-wide suspend too. If not, we have to find a new thing, I think. And the final thing I think might be needed is that some of these, if we intend to use suspend-to-idle, and we add more states to those to the array of states that we support. Some of those states might actually just map to system-wide suspend. So maybe we need a way to distinguish those states from the other regular idle states. So maybe some additional things is needed in the DT bindings for this. So that's what I had in mind, and this is designed from a top-level point of view. Or at this point, we are working on this as we speak. We're starting to hack a little bit. It's not supposed to be a whole bunch of code. It seems quite limited and quite simple to implement this. So yeah, we are more or less just working on this at this moment. What we are interested to know about is obviously if there's more use cases, as I said, and if you have some platforms that you find suitable for this, please come and talk to us, and yeah, we can discuss how to collaborate. Any other questions or thoughts around this? It wasn't that interactive as I hoped.
Yeah, okay, hello. In the examples you gave for the motivation, the selected state that should have been chosen instead of the deepest state, is that a static one, like it should always choose some other state, or is it dynamically variable, like sometimes choose one, sometimes choose another?
So the idea, I mean, that you based on the platform configuration or the platform characteristics, you define an array of states, and all those states has characteristics saying this is the exit and entry latency for this state, and this is the other characteristics for all of those states have characteristics. And when you do the selection, you look at what has user space specified, what is the deepest constraints, deepest latency that user space can accept, and then you look in that list and pick the deepest possible state. So that's the idea.
And during the running of the system, user space can change the desired latency.
Yes, based on some use cases that user space is aware of, it can put different constraints. There's another question over there.
So when we have devices that may or may not be wake-up capable, or where we have turn on or off wake, how could we tie that into the selection of a level?
Well, part of that is already supported today. Well, might need to extend, let's say, decision making about the states a little bit, because today I think it's just like if there is a wake-up configuration required for some of this in this topology, you simply don't turn things off. You just leave it in the shallowest state possible. So what you're saying is maybe that is not good enough, or you might want to allow some states even though you have a wake-up.
It certainly seems like it's a platform-specific thing,
yes,
where some devices will be wake-up capable even in the lowest power states.
Yes, definitely.
And in other cases, you would need to maintain some minimum level of power.
Mm. That's right. Yeah, somehow maybe there is some additional constraints that we need to look into to be able to specify, or yeah, we need to have some kind of information about the characteristics of the platform, so we can take the right decision based on that instead.
Yeah, because the problem there is that it's not a latency configuration by latency. It is configuration by
functionality
between different nodes in the system.
Yeah, that's a good point.
I just want to add to this point. I mean, if I'm not mistaken, in CPI, the idle states bindings allow you to specify power domain dependencies. I'm not sure if that code is used in the main line, to be honest, but I don't know, maybe it's something that you could use to augment the DT bindings. Just saying.
So dependency between domains.
No dependency between a given idle state and the power domain results.
Okay.
Just
Yeah, that could be interesting to have.
is the I don't think the kernel use the bindings, but well, there is precedent in a
okay.
CPI for this information.
Okay, that's good information.
I think I'm just checking the downstream kernel for Pixel, and I think it's similar to Bjorn's point. There's lots of other sleep states that are kind of, sleep, but you want to leave USB on, or sleep, but you want to leave audio on, or the cache on, or something like that. So, yeah, it's not just latency.
So the way, the current way to deal with that would be to model this in a topology way. So you can have states corresponding to different level of the topology, and you can make sure that some part of that topology remains powered on. For example, if there's like a devices that has some system wake-up latency, or it's a system wake-up configure for that. So that is kind of doable today, but it also depends a little bit on the platform, of course. Okay. Any further questions?
So mostly of the power management is done by the kernel. So, but is there any user space tooling to actually see how system-to-idle or system-to-ram is saving power? Like
you can there's sysfs and debugfs information where you can have a look at what states are entered and how long you stay in those states. There is even statistics about if you try to enter a state and fail, you get information about failures too, so to say. So there's plenty of information about that. There's part that is CPU idles specific, and then there's this power domain things. So there's two kind of information sources.
Thank you.
Yeah. All right. Thanks everybody for coming.